Allin-Wayra. It's a Small Sensors Atmospheric Science webinar series. Allin-Wayra is an IGAC activity focused on small sensors. So the word Allin-Wayra means good air or winds of change in Quechua. Did I say it right, Seba?
Absolutely.
Thank you. Pre-colonial South American native tongue. So our mission is to foster a diverse and inclusive global sensor community of practice with a particular focus on regions lacking air quality measurements and to advance knowledge through collaborative initiatives that build capacity and promote accessibility. So we have our co-chairs here with us this evening. I'd like to introduce Nicole and also Seba, who are the co-chairs of Allin-Wayra, and together with them, I'm part of the steering committee. Ike is also part of the steering committee, and I think Samara's here. Did I miss anyone else from the steering committee who is attending the session?
I think there's a few more, but I've lost track of everyone who joined.
Okay, sorry. I wasn't keeping track of the participants, but to the steering committee who are present, thank you for the support in this evening's presentation. If you want to learn more about Allin-Wayra, we would be happy to learn from your work, and we would be really interested to get to know your personal information. So please visit us in our LinkedIn or through the information presented here. And then, so this session is about best practices for calibrating local sensors in resource-constrained environments. We have two speakers, Dr. Ike Mead from Imperial College London, who has been instrumental in our work here at the Philippines because of our introduction to the Breathe London project. And also, I'm happy to have Emil, who is part of a research center also based in India. So we'll get really good insights on calibration techniques that were performed in the UK and also in India. And also, before we formally start, I'd like to invite everyone to submit your abstract in the upcoming AGU 2026. Shown here is the link to our session, the one that's being hosted by Allin-Wayra. And please remember that the abstract submission is on August 5, 2026. So we hope to see you there. So with that, I'd like to pass on the webinar to our first speaker, Ike.
You're muted.
Can you see my screen now and hear me?
Yep.
Yes.
Excellent. Thank you very much. Right. Well, thanks very much for this opportunity to talk to everyone. Today, I'd like to discuss some of the issues around calibration and transferability for lower capital cost sensing. I'm going to be using various terms interchangeably: small sensors, low cost sensors, miniaturized sensors. But I tend to think about them more as lower capital costs, in as much as we have to consider their operation and the costs involved with that ongoing correction as well. But please don't be surprised if I move behind the terms just because I'm getting a bit sloppy when I get to certain slides. Please note that I'm not proposing to answer the questions I'm putting up in the next slide. It's a 20-minute session. There's no way to actually answer it, nor do I actually think there's a distinctive answer right now. But I would like to maybe open up a dialogue with some thoughts. So, yeah, let me start by stating the two questions more clearly. The first question is around what makes a co-location period suitable for building a robust calibration correction model. The second is how do we extend, scale, or transfer this calibration model when references are scarce or limited? And there's a third thread I'd come onto at the end, which cuts across both questions, and I'd like to raise it, and that is communicating uncertainty. First, a few framing points to perhaps set some expectations. There is no, as far as I can tell, there is no single best calibration strategy. Depending on the use case, valid options can range from simple linear regressions all the way through to hierarchical or transfer learning models and some sort of hybrid physics statistical approaches. Better test performance does not automatically mean better transferability. What works beautifully in one season or city or one location may not travel well, even to the other side of that same city. Uncertainty is often undercharacterized, and that's risky if we've been using data to inform public messaging or policy changes, or effectiveness of any mitigation actions as well. And with that in mind, why do collocation, duration, and transferability matter so much? As we all know, we're in this technology-driven period where we have the potential to dramatically expand our environmental coverage, and that touches on things around social justice issues, ability to actually understand what our personal exposure may or may not be, looking at behavioral change at the societal level and at the personal level. Essentially, low-cost sensors can democratize environmental data, and they potentially fill global information gaps if used well. But outputs from these relatively low capital cost sensors are sensitive to a number of confounders such as humidity, temperature, fouling, and device variation. I would like to stress, though, when we're talking about low capital cost sensing, that's a whole family of approaches. EC and OPC are the two main ones we tend to work with, but there's also micro hot plates. You've got your metal oxide sensor. There's all sorts of ways to be doing it. So please take all of these things as shorthand, with the devil being in the details, specific to the instrument you're using and the way you're using it. I think it's important to reiterate that dense networks are only useful when data quality is maintained and understood. Having a number doesn't necessarily mean you have a data point which is of any use. But we all know that, of course. So consequently, the goal isn't just more data, it's more usable data. So moving on to what makes a collocation period, inverted commas, enough. A useful period, it's not a fixed number of days. It's essentially a period which captures the environmental range the sensor is likely to face in the deployment domain, be that temperature changes, humidity changes, concentrations in and of itself, and concentrations of cross interference. And also not just one set, so high temperature, high humidity, high ozone, say, it has to be high temperature, high humidity, and low ozone as well. So it becomes a matrix of range of variables that we need to try and constrain as best we can. And we just need to constrain our models with enough independent information. It's important to note that hourly air quality data, or some faster data as well, tends to move quite slowly. What I mean by that is consecutive hours add less actual information than you'd think. Or data is autocorrelated. The next data point is likely to be similar to the previous one. And the whole point of that collocation period is we want to basically develop a model based on that is stable and diagnostically acceptable. When I say diagnostically acceptable, I don't mean just that it has a good R squared. I think we've moved beyond that in our community. We need to be looking at other methods to actually say whether this is good and usable. So thinking in terms of effective information, representativeness, and stabilization rather than just calendar time. So that raises the important point, numbers versus content. So as I mentioned, air quality time series are often autocorrelated, so data sets may contain far fewer independent bits or pieces of information than just simple number of data pairs you have. On the slide, I'm showing a simple approximation for some sort of effective sample size, where NA is the number of observations and rho is the lag -1 autocorrelation. The brief worked example shows why this matters. Suppose we have 28 days of hourly, clean, gap-free, and evenly spaced data. Yes, I know, we can all dream. If we have a rho -1 value of 0.6, which is essentially suggesting that each observation fairly strongly resembles its preceding neighbor, this 627 hours becomes 168 pairs of independent data points on which to base your model. So suddenly we're talking about essentially a week of data out of a month of deployment, or a week of independent data out of a month of deployment. So how do we actually decide then how much is enough if we can't just say number of days? We could consider a collocation adequate when the effective information is reasonable for the use we have for it. We have that coverage across temperature, humidity, concentration ranges, etc. We can also look at where the performance gains are starting to flatten out and where our residuals start looking pattern-free. For example, for PM sensors, you want to make sure you've seen both dry and humid conditions. And for NOx-OX sensing, you'd benefit from windows that capture both daytime and nighttime chemistry, and then weekly traffic cycles. It's probably better to avoid a single stopping rule. Instead, we should be judging sufficiency using a combination of effective data point pairs, coverage that includes a reasonable, and I know that's not a scientific phrase, but a reasonable spread across, say, bins of temperature, humidity, concentration, and where our model performance gains are starting to taper off. Let's look at this last performance gains point now. Again, there is no fixed formula to rely on, but two practical checks that work well together, I think, are use of errors relative to the population mean and differences between the data and model predictions. So the first one, the errors. Using some sort of root mean square deviation approach, rolling, you can see improvements in errors over time. Initially, you'll see significant improvements, but then eventually, at some point, the curve will start to flatten out. And extra dots, i.e. extra data points, make less and less impact on the model performance in terms of its error. Similarly with residuals, you want to assess for any remaining structure in the data, in the residuals, that is. So plotting the residuals against fitted values, you should not see any clear patterns. A flattening RMSE trend suggests more data will add little to your analysis or model development, and structure-free residuals suggest the model has captured the main structure you've encountered so far. If either fails, you should either extend the duration of the experiment or improve the model, or both. I just want to stress, as someone who loves spanners, fieldcraft still underpins all of this. Good modeling doesn't fix poor field practice. Things, I know this is going to sound so simplistic, but things like synchronizing clocks, match sighting, considering stabilization, documenting interventions, all these things are still needed on the ground. And we need to be looking at our outliers. We need to be trying to find where data is really data, or where it's anomalous, or due to, say, power glitching out, these kinds of things. And we need to be thinking about our aggregation approach. We need to balance noise and detail. And we often go to hourly, although I do feel we should be going faster than that, mostly because hourly is what we've always done, and it feels about right. I've got hourly data. I'm not sure if that represents the environment effectively for exposure studies, but that's a very, very different presentation, and I'm not going to kick over that particular nest at this point. Using robust outlier detection limits our spikes, but we have to be careful how we do this. I mean, using a rolling Z-score approach is reasonable, but we have to be careful what our parameters are when we do that. So now we've fixed our collocations. How do we cope when our reference data are scarce? Scarce, not scared, scarce. In many deployments, there's no local reference, or we've only had a brief collocation, or we've used a reference in another city or another country even. Sometimes there's only satellite or analysis data available. So the main challenge shifts from fitting a curve to ensuring that fitted curve or behavioral transfers from the calibration domain to the target domain, i.e. avoids a mismatch. An increasingly common tool is using some sort of pooled global baseline based on calibrations from many cities over many sensors, and a number of manufacturers are starting to more effectively implement these as they collect more and more data. With this approach, each site can start and be, inverted commas, again, the non-scientific term, sensible on day one. And then you can adjust this locally with smaller assessments. However, this probably will not cover unusual conditions, such as, say, rapid monsoon onsets or specific types of local biomass burning, that kind of thing. And care needs to be taken with any local updates if they're based on very short, potentially unrepresentative windows. So all this can be paired with some sort of planned recalibration approach based on some sort of set cadence that you've decided beforehand, or on triggers such as residual growth or input distribution shifts as you move into different seasons. fundamentally, we need to be matching our transfer architecture to our realities around reference availabilities, communications, compute overheads, and staffing. Some architecture examples include some sort of anchor and rotation, using a few trusted sites to act as a calibration station, with each node visiting for a short stay every month or so. This is relatively simple and traceable, but requires good and robust logistics and management. Also, you can get drift between visits, so that needs to be monitored as well. You can try some sort of hierarchical pooling using cloud-based data. In this approach, a shared cloud model covers the network, with local data being driven by local adjustments. These local anchors can inform and improve the shared model, but you are moving away from direct calibration as you go down this list. Similar to this is using some sort of transfer learning, where you train your model somewhere else and adjust it at the target site based on its performance. Think of regional reference facilities here, such as AfriSet, or the Air Paris activities on regional facilities that people can bring their sensors to in this context. In terms of strategies, this is about what architecture of frameworks are theoretically possible, coupled with what is actually doable and maintainable. That's important. It can't just be one-off, or shouldn't be just one-off, but it has to be maintained on the ground in your specific chemical environmental scenarios. So several architectures can work, and they need to be chosen by context, not necessarily a fundamental ideology. But even with good frameworks, comparability remains a big challenge. So we do need to, again, going back to my fieldcraft slide earlier on, we do need to keep some practicalities in mind, which can be overlooked. We need to better preserve our raw and our ancillary data, especially when we're using data which has been, shall we say, data which has been updated or calibrated or validated or in some way corrected offline in the cloud. Losing that raw data can often preclude you from going back and looking at data when you have more data, or when you have a better approach to improving your data set. So I think there's value in having that raw signal, as raw as you can get. If you can get counts or voltages, all the better. We need to be contributing to the literature to support some sort of pool-based model. I don't mean by supplier, I mean as a scientific community. And I don't just mean with success stories, but also with the issues we've encountered, warts and all. The more information we have, the better. We need to make sure we adapt to local conditions and needs. So expanding our plans based on transferability from the start, as opposed to doing a co-location and then later on going, well, what do we do now? It's, in my view, more valuable to, if you have a fixed funding level, to perhaps reduce the number of overall nodes to increase the amount of calibration validation you've built in from the start. So it's not just more sensors, but more planning. And we need to continue our validation studies locally, documenting our decisions and maintaining quality after the deployment through things like drift detection, outlier checks, periodic refreshes, and perhaps confidence flags. I'll come on to that later. I'll touch on machine learning tools now, as we all essentially have to. Machine learning has grown to capture various complex effects, but complexity doesn't guarantee transferability or a smaller uncertainty. Methods such as random forest, gradient boosting, SVR, or neural networks can help capture nonlinearity and interactions and drift patterns, but this can end up being a very, very effective tool which can only be used in the domain in which it was trained. High in-sample scores do not remove uncertainty, and interpretability and comparability still matter. I feel we need to use machine learning as a tool within some sort of disciplined validation approach with uncertainty qualification and clear communication of limits. The next slide I'll bring you is a tropical example which shows why evaluation design changes what works in a particular domain space. So, highlighting this recent work from our friend Professor Richard's group here. In this Metro Manila example, the study compared three split strategies, so chronological, stratified, and random block. It showed that performance of the model then was was very dependent on how the data were initially split. In that setting, interpolation coverage was about 97%, and the Gaussian mixture regression performed very well. But the key lesson isn't which algorithm won, inverted commas, it's how you partition and test, how that testing strongly shapes the apparent performance. So again, we need to consider calibration as a life cycle with ongoing QA/QC, not a one-off. I'm not going to dwell on this slide because Emil will be talking in far more detail about drift and better detail about drift and whatnot. But broadly speaking, drift is subtle and we need to track it. We can't just take drift values from a data sheet and say that's what we're going to apply. We need to be monitoring it ourselves. And it's a continuous effect. Anomalies also, they don't fit any specific patterns necessarily, so data needs to be monitored. I'll share all references for equations and whatnot at the end. But overall, calibration is a life cycle, not an event. And now on to a little hobby horse of mine, communicating confidence. I think we need to publish or at least make available more than our concentration data. I think we need to consider providing guides to data confidence and uncertainty to prevent some sort of overinterpretation and to clarify not all nodes are equally reliable all the time. It sounds frightening, but if we're transparent about this, I think we can build trust. Transparency is important in building that trust and also building our understanding. It also allows continuous collegiate improvement. Importantly, and obviously, this does not fix analysis, performance or analysis limits, but it does make them more visible. Related to that is explicit uncertainty. In practice, uncertainty is often undercharacterized because point estimates are much easier to publish. Uncertainty often varies with conditions rather than staying constant, with humidity sites, and it drifts. And extrapolation beyond the training regime will add to that uncertainty. We should perhaps be better quantifying and communicating our uncertainty with, say, prediction intervals or some sort of Bayesian or conformal bands, and adding flags that widen intervals out of our calibration distribution testing. Networks become more useful, in my view, not less, when they acknowledge where uncertainty is wider or changes. And I will finish off. I don't think there's a one-size-fits-all calibration. I hope I've not disappointed anyone, not telling them, right, you've got no reference sensors, or you've got one reference sensor, do this. If you've got three reference sensors, do that. I think actually we need to be thinking about adequacy, which is better judged by coverage, independence, and stabilization and residual diagnostics than by a fixed number of day counts or an approach. Several viable network scaling pathways exist. Pick what matches your references, communications, compute, and operations availability. Ongoing, not just right at the start. Use of AI and machine learning is growing, but that does not remove uncertainty or guarantee transferability. We still need to be disciplined in that respect. More an explicit uncertainty assessment and confidence communication, I think, are valuable and needed. But again, as a person who loves spanners, we shouldn't overlook just basic good practice. I've been involved in studies of my own where we've looked back and gone, we didn't synchronize that, or we didn't save that data, or whatever it happens to be. And that makes our cross-site comparability weaker. And the goal, as always, remains the same. Dense networks that are transparent, interpretable, and decision-ready. Thank you all for your attention. If any of this has interested you or your collaborators, please consider sharing the AGU session, which Richard has put up in a far more pleasant slide than mine. And I would like to thank the chairs of Allin-Wayra and all the steering group members for all the fun and very interesting conversations. Hideous slide of references. Thank you.
Yeah, thanks, Ik, for this presentation. Yes, questions? We'd like to hear from our audience this evening. Maybe I can start off with one question. Ik, in your work so far, how often do you change your calibration model, say, in 1 year of operation?
Well, that depends. On some of our deployments overseas, we have a periodic sort of a cadence of recalibration, and we try and use that to back correct our data. In the Breathe London Communities project, we have a live daily recalibration of our sensor nodes based on transfer calibration from a number of anchor nodes alongside reference sensors. And that is calculated based on hourly data and then every night reapplied to the last day of data. So you end up with this rolling correction. So we can only do that because we have the infrastructure to do it. It's not possible in many places. So some studies we've done in the past have been very successful based on an initial pool co-location and then a end pool co-location, and with some sort of intermediate management of residuals and errors as you go along to remove sensors as they stop meeting the criteria that you set for them. So it's very much horses for courses.
Yeah, okay. Really, really insightful, because I think this is an important consideration, especially for those in the audience who will be deploying their own sensor networks in the future or currently deploying them, so that they know how they can report their data quality processes, so that when it will be used by government institutions, there is more trust in the data that we are using. Yeah. Other questions, guys? How do we break the ice?
We have a question from Samara in the chat. This daily calibration you make, does it require a reference instrument?
It actually requires 19 in our case, or rather, sorry, 17 in our case, where one of them is triple located. And the idea is that with those selected reference sites, we are trying to cover as many different domain types as we have across the Greater London area in as much granular detail as we can. So that is a bit of an extreme case because we have, 70 plus reference sites, and we have those ones that we operate and we can run and we can get to them easily, and we have all that logistic support around them. But we've done some experiments where we've reduced that number. I mean, in a hybrid sort of mathematical sense, not on the ground. We've reduced the number of reference sites across different numbers of reference type domains and see whether that transferability drops fast or slow. And it's quite clear that you have a rapid increase in the number, the performance of your correction model as you have a better representation of the nuanced environments in your system. You're not assuming a homogeneous environment across your whole domain.
Yeah.
The better you can cut that domain up into different types of chemical, physical, behavioral groupings, the better your calibration is, your correction model can be, potentially can be. I should be careful.
Julius, do you want to unmute or type in the chat?
Hi,
Hello.
can you hear me?
Oh, absolutely.
Go, Julius.
Yeah, I'm Julius. I'm a colleague of Richard. I would like to ask, how do you account for like meteorological factors and, for example, seasonal variations when you're doing collocation?
That's a very good question, a very difficult answer. Essentially, we're in the middle of writing we're in the middle of submitting the paper. We, using 3 or 4 years of historical data, we quite clearly see a difference in the calibration values, or shall we say regression values we use for different types of calibration, depending on which season you do your co-location in. And it all boils down to the same point. Your calibration or your co-location period has to cover, or should cover, as broad a range of the expected conditions you're expecting to see with your chemical species and your humidity, temperature, meteorological factors, or burning season or monsoon, whatever it happens to be. If it doesn't catch those, then it's unlikely that your model will be able to adequately represent them in your correction model. That becomes harder and harder to do when you have edge cases such as short-term monsoon, short monsoon breaks, or rapid onset of a rainy season and rapid flooding type events expected, or volcanic events, whatever it happens to be. You need a certain amount of data in that regime to be able to use your model to correct for it. So this goes back to my point about multiple approaches used together is probably the way forward to go, because then you can say, right, I've started as best I can using this, say, a global approach. It is sensible, it is stable, it is working. And then when you encounter either edge cases or differences between the model environment used and the target environment it's being used in, you can start improving on that model using local analysis. And then you can add that to your model post fact and share that with the wider community and say, right, we encountered this new regime or different regime, and our factorization didn't work as well for that regime. at the time. But now we've taken that into account and we can better characterize for it next time. So it makes it very difficult to get real-time data because there's a lot of an assessment to try and get to that point. But it's all about covering an adequate or representative range across a number of species and also their relation to each other. So, as I said, it's not just a list of all the temperatures and all the humidities. It's all the temperatures at all the humidities and how they interact with each other as a sort of a matrix.
Thank you.
Thanks for that question, Julius. We have one chat question here. So I think this is about not having any reference analyzers. So what do we do with that?
I was waiting for that particular question. I mean, we could quibble, we could split hairs and say, well, there's always some sort of calibration, the one done at the manufacturer to make sure it passes some sort of QA/QC. But that's an unfair answer, I feel. In the earlier days of deployment of these sensors, you could literally have a sensor coming off the conveyor belt and have basic electronic calibration only, and the numbers are very, very difficult, and you have to post-process to get your data. Now, a large number of sensor manufacturers and research groups are generating so-called global pooled models or hierarchical pooled models, where you have as many, say, cities or seasons of data from that type of sensor have been used to generate some sort of averaged out global correction mechanism. And that can be suitable for use where you don't have any calibration whatsoever. You can also bring in things like reanalysis data. You can bring in things like satellite regressions, mostly for long-term baselines, not for acute events, of course, because the timescale and the granularity of the data isn't sufficient for that yet. But that goes into my uncertainties point. It's not about getting the best data. It's about getting the best data that you can get that is answering the questions you need. And if you have a data point and an uncertainty around it, that can still provide a lot of information to answer the questions that you need answered scientifically or socially in that domain. But we can't get away from the point at the moment. Technologically speaking, the use of the broad, small sensor community of sensing sensors type things, or however you want to describe it, will at some point have to be or should be linked back to some sort of known reference at some level to improve your data. And that's just a reality of the game at the moment. And even if you just have a traveling sensor visit for a short period, or you co-locate all your sensors with the manufacturer right at the start against a reference there, or you use their globals, there are ways to improve the data, not fix it, but improve it. Fix is the wrong word. There's no such
Yeah.
thing as perfect data. I mean, we are comparing against reference sites, and a lot of the reference calibration values given for humidity on particle sensors can be, 20% of the signal. So ground truth, which we're comparing against, isn't absolute either. So uncertainties, go to the square as opposed to additively. So it gets tricky.
Yeah. Thanks, Ik. We have another question coming from Jenny. So she's from Colombia, and currently
Hello.
she's deploying a low-cost sensor network in Bogota.
Mhm.
Her question is about collocation duration.
Mhm.
So the master node is about 800 meters away from the only reference station that they have. So the question, sorry, I tried to shorten the question, but do you have any recommendation on the collocation strategy given the 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 the, the distance between the referent and the master node? So she's asking whether 3-month data is sufficient, or will you have any other recommendation?
In a situation where you are that many meters away from a reference site, you have to understand that there's a distinct possibility that meteorology will mean that you have essentially different air parcels or air masses at the inlet to the reference site and at your sensor. And those differences are going to be more pronounced when you're looking at short-term data, so short-term peaks, individual vehicles, someone smoking nearby, rapid changes due to a plume passing across. But there will be far less difference when you're considering a regional background, which is much more slow moving. or nighttime chemistry has taken effect, you're going to get a bias towards correcting to the long-term changes relative to the short-term changes. Best practice, I hate using the phrase best practice because that implies that we've come to a point which we can't improve on. We want to be trying, I mean, you look at the US EPA guidebook, it's a fantastic resource, and there are many others. And Nicole's publication on the same thing is a fantastic resource to look at. But what we're trying to get is, as near as possible, the same, inverted commas, error at the sensor manifold for the reference site and at our sensor. We want to get a matching response times, the T90 in our cell, how quickly we're turning over our air. We want those to match as much as we can. And in terms of duration, again, going back to one of my earlier slides, it's about how much representative data can you say you've collected relative to the domain you want to deploy in later on. But you are going to be building in biases and potentially offsets because of the co-location being a bit more sort of co-location at that sort of distance. It's not a direct one-to-one. So you're going to be looking at different sampling regimes essentially. So that ties into the aggregation approach you use for your calibration model. Hourly aggregation versus at that sort of distance, depending on your local topography. You could be even looking at daily aggregation to try and see where they match because of that distance. But maybe you need to be tying in a wind assessment to say that when the wind direction is in this way, i.e. over a certain speed and from a certain direction, which means that both your inlet at your sensor and your reference inlet are more likely to be experiencing the same airflow, air mass. I mean, it's a fascinating problem to try and solve. Please, it'd be very interesting to just drop an email. It'd be lovely to talk about it in more detail.
Thanks, Ik. I guess we can at least answer the last two questions before we pass it on to Emil. This is from Glidine. I hope I pronounce it properly. How do you decide the minimum acceptable calibration dataset size before deploying your local sensors in the field? Also, in areas without nearby reference grade monitors, what is the most defensible calibration strategy for low-cost air quality sensors, and what minimum QA, QC steps should be completed before the data are used for public communication or policy decisions?
That's very good set of questions, but a very difficult one to answer. I can only fall back on maths, my old friend, to get me out of trouble, statistics. Having enough data to let's say we take our regime of our expected regime in our domain of temperature variation, humidity variation, and concentrations across a big matrix of bins essentially. Have we covered most of those bins? And most is used in its non-scientific way, as in most, define it as you will. Say 70% is one that is often bandied around in some report. And have you covered 70% of your bins? And do you have a certain number of replicates in each bin to say that you're not just one peak, but you have enough data to say this is the typical peak or the typical behavior in that little bin in my big complicated matrix? So let's say we can use that number. I'm not quoting this number as the one to use, but it's one which is I've seen in the literature a few times. You've covered approximately 70% of the range you're expected to see and the variation within that matrix of species that you're expecting to see. And then you want to be able to say, I've got enough effective data points. So data points which aren't correlated, autocorrelated to other data points to say that I've got a statistical coverage of how many sensors I want to use. And the example I put up is 4 weeks sounds great. And a lot of people use that as almost a hard and fast rule. But 4 weeks of data which is highly correlated is actually 1 week of usable data for training your model. And that's not a nice message to send because it means we've got to do more work. But it does tend to push us towards the idea of having a co-location or having an initial calibration, which we then improve on as our network evolves and grows. So using some sort of anchor if you can, or if there's no reference site, sending a sensor overseas or to a partner to calibrate as best they can and send it back. All of these things will add uncertainty, but they're all ways to reduce overall network response uncertainty. And again, I go back to my point of saying, well, wouldn't it be great if we could say for policymakers or public, this data is as good as we can get it based on the conditions we have. And you can advocate for getting more reference sensors using that as an evidence base. But you can also say that this data is not, we want to get away from the world where people are assuming that small sensors or low-cost sensors, however you want to define it, are usable for screening studies only. They're not quantitative, they're only qualitative. The whole point we're trying to do is quantify our uncertainty band tube around what our uncertainty surface is around our data points to be able to defend it based on the maths and the physics of it, the chemical physics of it, so that when we do put it forward as evidence for whichever particular group, they can't come back at us and dismiss it. But we can defend it up to a point based on what we've done. So it's not a sort of a simple binary situation of we did it this way, therefore it's okay. It's much more of a spectrum, as in we did it this way, therefore it's probably going to be more useful for these situations, but it might not be appropriate to use it for this other situation. And I think that's far more valuable than trying to die on the hill of small sensors are as good as reference sensors. That is a hill I don't think any of us are reasonably expecting to fight and win on. It's not what they're for. It's not how they're used, in my view, of course.
Yeah, thanks. Before we acknowledge Fernando, I'd like to just give Florentine's question some airtime. So, have you come across any new technologies to replace OPCs? And what about new technologies for ultra-fine particle monitoring with local sensors? You have any inputs on that, Ik?
I'm not going to name any names, but there are a number of manufacturers who are putting out some very good ultrafine or approaching ultrafine sensors. I think what we should be asking ourselves is almost the other way around, as in, what are we actually sensing when we use an OPC? Just because it's reporting PM1, PM2.5, PM10, is that what we're actually reporting? Or are we using scaling factors to get between those things? And that's not a problem as long as we acknowledge it and understand what we're doing. Do I know of any new technologies on the horizon? Ask me again once I've put my investment money into whatever company it happens to be, because that would be if there's a small $20 sensor which did ultrafines beautifully, I think there may be a global market. I would strongly recommend going to the literature. Look at Sensors and Actuators B, for example. There's some fantastic examples of new sensing or new ways of using existing technologies. There's a lot of people in research groups miniaturizing very effectively and using things like machine learning on top of that miniaturization to help solve for some of the problems. It's a very active, very quickly evolving world. And there's a danger that things can be overstated potentially in terms of how good they are, because the motivation it can be towards, shall we say, we need to stay on the side of the angels, that our motivation is about getting the best data possible. So it's a tricky question to answer. But again, if you want to discuss it further and talk about it in a different forum, please do get in touch for your specific use case. It'd be great to have a chat about that kind of thing.
Yeah, thanks, Ik. Maybe we can have this last question and then we can pass the session to Emil. So, Fernando.
Thank you, Richard. Hi, Mohammed. Well, we live in La Paz, that is at 3,400 meters above sea level, and we have a bunch of local sensors to measure particle matter. However, we don't have enough good results resulting from our calibration method. I saw your presentation, it's very interesting, and we follow it almost all your suggestions. We are near the reference sensor, we have enough weather conditions related to relative humidity and also temperature and sun condition and windy. But when we have this correlation along with our local sensor and the reference one, we don't get a good transfer function. The correlation is not so high as we read in the reference or the previous studies that people did around the world, because they just make a linear correlation and they have a good transfer function, but it's not our case. So I want to know if you have any additional suggestion to these extreme conditions on which the low density air maybe is a matter.
I mean, the Paz, my wife actually lived there for nearly a year, years back, and she used to tell me about the extreme conditions that, before we got married, the extreme conditions she experienced in her time there. The interesting thing about where you are is obviously your altitude, and the pressure relation is going to be far more important for you relative to, say, someone in Holland. And manufacturers are, when they build a sensor, are trying to build a sensor which is more globally usable. So perhaps I brought up this slide here because the little graphs, the very simplistic calibration, curvy kind of graphs, I have a strong suspicion you're sitting on the red line, the crushing reality line, that is nonlinear response outside of the operational range of the particular instrument that you're using. And using additional terms might help, but you are going to be working in a slightly different temperature, humidity, pressure regime than most people in the world. And by the way, congratulations on what sounds like a very extensive setup for your reference work. That's not an easy thing to do. So we should all be, congratulating you on that front. So yes, there are probable problems with where you're measuring, and especially with the composition of the dust you're likely to be seeing as well, and the phase it's in, accumulation phase, that kind of thing. And the humidity correction also of your reference site needs to be considered, because the humidity is going to very, very much affect that too. So you're correcting something which is struggling outside of its performance envelope, potentially against something else which is struggling against its performance envelope as well. Please, again, drop me an email. It'd be fantastic to talk about the situation specifically. But I think what you've done very nicely is highlight the point of appropriate approaches in whichever particular domain we are working in. And I think it's far easier to do it in London than it is in La Paz. But please do get in touch. It'd be fantastic to chat more about it.
Okay, thank you. I just want to say that along this instrumentation, these local sensors, they behave very well. The correlations is very high, and also the bias
Yeah.
is so low among them. But once I compare with the reference ones, the issues started.
Well, you know what? Maybe we should be looking harder at the reference site. Maybe we should be looking at that a little bit more. Maybe this could be a clear win for the small sensors. Small sensors 1, reference sensors 0, to use the footballing thing at the moment. Perhaps. I'm not casting aspersions, but it would be lovely to talk more about your particular situation.
Okay, thanks, Mohammed.
Yeah, we'll be winning the World Cup soon. Thanks, Ik. As I said in the chat, thank you very much for a very engaging session. And now, let's have Emil, our colleague from India, who has loads of more information to share with us with their collocation experiments. And this is for a different type of environment and climate. So take it away, Emil. Thank you.
Thank you. Thank you, Richard. I'll just share my screen. Yeah, so can you all see my screen? And yeah. Okay, yeah, cool, thanks. So first of all, thanks to Allin-Wayra for inviting me for this webinar. And so today I'll be talking about our experiences when we had developed a sensor evaluation and training facility in India, and how we experienced what are the different insights we got while we were evaluating few sensors. So the INDISET, or the India Sensor Evaluation and Training Facility, is an independent and standardized testing for air sensors in India, and we had reference gauge instruments for PM2.5, PM10 gases, weather station. Then we have the black carbon measurements using AV33 or accelerometer. And then we also have ACSM with real-time chemical characterization, exact with metal characterization. So in INDISET, we mainly conducted two main sensor evaluations. One was in phase 1, which was a long-term sensor evaluation, which was in the year of 2024, where we looked into 5 sensor vendors which was commercially available in India. And these sensors were integrated with different types of sensors, like we had the Terra sensor, Plant Tower, Sensorion, Alpha Sense OPCs for the PM measurements, and for the gas measurements, we had the Alpha Sense and EC Sense gas sensors. Then phase 2 sensor evaluation, it was two biseasonal sensor evaluation, which will be conducted in partnership with partnership with AirParif and AfriSet as the AirLab Micro Sensor Challenge. So the phase 2 sensor evaluation results will be announced in September, while we have the phase 1 sensor evaluations and what we understood while we were looking for a long-term sensor performance. So before we jump into the sensors, sensor data in depth, let's see what are the different levels of sensor data that is available to us. So firstly, it's the level 0 data. This is something which I've taken from the Schneider et al. 2019. So level 0 data means the room measurements. That is, say you have the voltage corresponding to each measured quantity, like for electrochemical sensors, or it can be the voltage corresponding to the light scattered in nephelometers. Now you have the level 1 data, that is the factory calibrated data. So here everything in the millivoltages will be converted to your microgram per meter cube or ppbs in the case of gases, or it can be the pm mass in the case of pm sensors. Now you have the level 2A and 2B data. So 2A is the data where the sensor data where you are calibrating it by adding different cross-sensitive parameters, like say for in the case of NO2, you are putting up adding the ozone sensors or the temperature and RH effects to your calibration models. Now, if you are applying it within you're using the sensors from the same box, that is the temperature and RH report by the sensor, then that will be level 2A, and level 2B is the same one if you're using the reference instruments data to build your calibration models. Level 3 and level 4 is using the data that is using different proxies as well as some modeling assistance, like you try to make the spatial maps and this, or it can be the proxies for certain gases, like for NO2, you can consider the emissions or so. So here in our coming slides, we'll mainly focus on the level 0, level 1, level 2A data, which is majority of us mainly use. So firstly, let's see this is something from the performance of gas sensors over 6 to 8 months. So here I'll explain it in detail. That is, so here you have the NO2 concentrations reported. So on your y-axis, you have the NO2 concentration from the reference instruments in ppb, and on the x-axis there is the NO2 from the it's a level 0 data which you get, or the level 1 data which you're getting from the sensors. So the first vendor has an alpha sense NO2 A series, and the net voltages are being reported. Then second vendor has an EC sense TB600, where you have the NO2 in ppb reported, and the third vendor has an alpha sense NO2 with the B series, which is also the net voltages. So you have the auxiliary minus auxiliary electrode minus working electrode, which gives net voltages, which is recorded here. So here the first row is the January-February month. Then it's a seasonal plots. So then on the second row, you have the March, April, May, which is summer months. Then you have the third row, that is the June, July, August, September, which is a southwest monsoon time in India. So during this, what you see is that, and this orange line over here is the initial distribution of the plots, which I've just outlined. So initially what we noticed is that, considering the vendor 1, there is a slight linearity for the net voltages in the initial periods, but as the season is coming to monsoon, where you have the lower concentrations of the reference station, say that when the NO2 is below 40 ppb around, your net voltages are just getting as a big clump. It's getting so that means your sensor is actually not recording properly when you are having a very low concentration of NO2. Now, when we look at this vendor 2's EC sense TB600, the difference is, so here the values are in ppb. So initially there is a linearity which you can correct it. With the slope correction, you will be able to correct it. But what you see again is that when the lower concentrations are coming, it is it is getting clumsier. But at the same time, one important thing to be noted here, when it is the ppb values you're comparing with the reference instrument. So here, say EC sense TB600, generally, like even when your reference instrument is recording 100 ppb, your sensor is actually even recording 10 ppb, or the maximum it is able to record is nearly less than 25 ppb in majority of the cases. So that's what we noticed when we were evaluating the EC sense gas sensors. Now vendor 3, which is having a B4 sensor, what we noticed here is that here again there is a clumsy, like it is getting more the points are becoming I would say that it's clumsy. The points are becoming crashed to the bottom one. from us, like it says like month wise it is coming, which you can actually see that it may be due to the sensor aging after 6 to 8 months of operation. Now let's see it in the respect of the ozone sensors. So same vendor 1, you have the alpha sense A series, then vendor 2 with EC sense TB600, and vendor 3 is having an alpha sense B series with you. Same way you have the in the x-axis, it's the level 0 and level 1 data reported from the sensors, and on the y-axis, it's the reference instrument ozone values. The main thing to be noted here is regarding the vendor 3. In the initial phase itself, there is no linearity with this data points. So there is no linearity means the moment we have started recording or started looking into the data itself, the sensor has actually gone bad. So the thing is, in the case of electrochemical gas sensors, the major thing is it's not from the time that you start recording that the sensor is aging. It's from the time that you actually open the packet, the sensor aging starts. So there is a main thing that suppose we hadn't noticed this initially, it's just going to be same way, like somebody is going to just evaluate, and also it can be that at this moment you are building a calibration model. So your sensors raw data has already gone bad, but still you will be building a calibration model. So there is always an important need that even before you start the calibration, the moment you have the sensor in hand, the first thing you need to do is to have a collocation with the reference instrument and see if you are actually in a stage where the sensor is actually functioning. So now let's see, I'll just talk about how we started evaluating the long-term performance of these sensors. So as I mentioned, the collocation is the first step, and that should be with reference instruments which are well calibrated. So here in this set, we follow the US EPA protocol where we evaluate calibrate the reference instruments. Like for gas sensors, we have for 14 days zeros check and span check, and then for the case of PM monitors, we do it every month. So we make sure that our reference instruments are actually well calibrated before before comparing that with any sensor. And then, as I mentioned, there is an important need that you need to first initiate collocation is required. Say it can be 4 to 6 weeks, or it depends on, like, say if you're considering, say, ozone, initially, like ozone in a particular season, we know that within it is mainly having a diurnal pattern. So like you have the higher ozone concentrations in the afternoon, lower ozone concentrations in the morning or in the evening. So that means or in the night. So that means that there is a diurnal pattern is what is mainly driving the ozone. It will be similar throughout a week or 2 weeks. So in the case of ozone, even within a week, we might be able to get a good data set. Also, while you consider, say, NO2 concentrations is mainly emissions are mainly connected with the vehicular emissions. So there might be peak traffic time, there might be low traffic time. So if you're able to capture, or the weekends, weekdays, or if you're able to capture such a good collecting data, then that itself becomes a actual evaluation of the sensor. So as it mentioned earlier, there is no particular time that, okay, you have to do it for 4 weeks or 2 weeks or enough. If you're getting a good set of data points with you, then that's it. Now, the other thing is, now you need to see the sensors aging and drifting, and that generally, at least we should be doing collocation with the sensors, with the reference instruments every 6 months to make sure that you're in the right place, because you don't want to do it every month, because you are already putting the sensor in the site and you want to capture as much as possible from the sites. Now, how do you deal with this data? So from the sensors, we get the data in either it can be from the manufacturer API, which you will get the JSON files, or it can in the JSON format you get it, or it can be from the SIM cards you get the data, or it can be from the manufacturer dashboard that you're just downloading the data. So whatever the data you have in hand, the first thing is data standardization. That is, you need to convert the data into local time, because your reference instrument will be actually capturing the data in local time. And the other thing is, different sensor manufacturers or vendors, they'll be supplying the data in different units. Sometimes the manufacturer might give you the NO2 values in microgram per meter cube, while your reference instrument is recording in ppb. So make sure that you are putting it in a standardized units, and the parameter names that we should ideally know which level of data you are handling. Is it the millivoltages with you, or is it or is it the level factory calibrated data that is coming to you? And another thing is that whatever the data that comes to you, make sure you are having it at least a 1 minute interval data, because sometimes certain sensors can even give you 10 seconds data, which you actually do not want, because sometimes it just be some noise that you're getting in hand. So ideally, at least at a 1 minute interval, we can start looking into the data. And then while you're looking into the data, the main thing is the data cleaning. That is, you can remove the data which is having less than 75% data availability. Say in a day, if you do not have 75% data, then that's actually not going to give you anything about that particular day. And the other thing is, you don't want a PM sensor reporting minus 5 microgram per meter cube, or a PM sensor reporting 3,500 microgram per meter cube. These are out of thresholds, and then those values need to be removed. Then we look into, for comparisons, in INDICET, what we follow is a 15-minute averaging for gases and 1 hour averaging for the particulate matter, because for PM, our PM monitor was functioning as a 1 hour average. So we estimated that comparison with our sensors also. And everywhere we do an aggregation, we always maintain that at least 75% data is available. And once you have this data with you, you merge the data with the reference instrument based on the date time, and then you look into different metrics. So this is metrics. This is adapted from the US EPA, where you look into the precision bias, the precision. That means, suppose you're having, say, 5 to 10 sensor boxes from the same manufacturer. You want to compare the sensors with each other, then you look for the precision. Or it can be the bias or linearity and error, which you compare each sensor box to the reference instrument. So in addition to the different metrics which USEP has introduced, we have actually added three other metrics. 2 in the case of precision, that is a correlation among sensor. Say you have 3 sensor boxes, sensor 1, sensor 2, and sensor 3. Now you can actually look into the correlation of sensor 1 to 2, 2 to 3, and 1 to 3, and then see if that range is greater than or equal to 0.9. This is something which we have looked into, and which we have noticed that can help a lot, in addition to the standard deviation and coefficient of variation, which the USEP has recommended. Similarly, we also added another metrics, that is the CVM, bias-corrected CVMA, in addition to the RMSE and NRMSE for error calculations. So, but although we have all these metrics in hand, in the last 2 years, when I was working with different sensor manufacturers and with certain stakeholders, government stakeholders particularly, what I noticed is that majority of them just look into just the value of R square. Now, and they say that if my PM sensor is reporting greater than 0.7 of R square, then my sensor is working fine. Now, I'll let you know why this cannot be considered, like you should not consider single metrics and decide your sensor performance in the coming slides. So just wait for it, and we'll discuss on this. Now, I'll just move to the next part, that is the development of calibration models. So as I mentioned, we had 5 sensor manufacturers which we were having. And out of this, we were having like at least minimum of 5 sensors from each of the sensor vendors. So we collocated this these sensors with reference instruments for around 4 to 6 weeks at INDICET. And then what we did is we split the collocation data into the training set and the test data in an 80:20 form. So you have the 80% of the data is the training data. So what we did for this is that we developed generalized and sensor-wise models. So generalized model means that for a particular vendor, you are actually taking the median of all the sensor devices in that particular vendor and then making a generalized model for a vendor. So say, and when sensor-wise model means for each sensor box, whether it is the vendor A or vendor B, you have a particular single sensor model. You do not consider the vendor, but just consider it as a sensor. So these were the 2 different types of models we worked out. And also we used various algorithms for developing these models. So the various algorithms we tested over the year was multiple linear regression, quadratic regression, support vector regression, random forest regression, and XGBoost regression. And once you have all these 5 models developed, now the confusion is which model would you actually start looking into, because you have to put the sensor in the site and start measuring. So the initial method that we used is that we gave a score, which is considering the bias-corrected MAE, RMSE, and the Pearson correlation R. And in detail, we have actually published a report where we are talking about how we developed this calibration model in detail. So any of you, if you're interested, you can look into it. I'm just covering it and going right now due to lack of time. And another thing is that while we were building these models, we actually looked into the different parameters that can affect that particular parameter. Say that for PM 2.5, generally PM 2.5 gets affected by the hygroscopicity. So definitely we looked into, we tried to give a model input as the RH. Now, when it comes to the gases, we looked into the cross sensitivity. So we had the NO2, ozone, CO, and additionally we also had the temperature also along with this. So one main thing we noticed, we did that certain sensor boxes had plant tower sensor and Terra sensor. Along with that, certain sensors even had an OPC, alpha sense OPC with it. So we thought that why don't we do a trial seeing how a hybrid model can work. That is, you are considering the PM1 value from a plant tower, PM2.5 minus PM1 value from OPC, and RH from the particular sensor. So this is a hybrid model which we applied. Now, there is also something which we did is the PM10 from plant tower, but actually using a PM10 from plant tower can mislead you in many ways. That is what I'm explaining with these plots. So here, on the top panel, you have the results from plant tower. So first here you have the PMS 7003 series and PMS 5003 series. And on the bottom panel, you have the results from Alpha Sense OPCR2 and from different two vendors. Now on the x-axis is the PM10 reported from the reference instrument, and on the y-axis is the PM10 reported from the sensor. And the colors of these markers are PM2.5 by PM10 ratio. So the lower the PM2.5 by PM10, more coarser your particles are, or more coarser is your particle composition. So that means the magenta color means you will be having high coarse particles in your environment. So what we notice in the case of plant tower is when your reference is reporting, say 100 microgram per meter cube, your sensor is actually reporting PM10 less than even 50 microgram per meter cube in the case of plant tower. So that means there is an under-reporting that is happening from the plant tower. So now if you're putting a plant tower sensor in a construction site, your construction site will be ideally like that's a coarse particle area, but your sensor will say everything is fine because you're almost 50% lesser is what you are reporting. Now that doesn't happen when you are using an alpha sense OPC, because alpha sense OPC, as you could see here, there is actually there is no variation with respect to whether it is a coarse or a fine composition. So what we did is we tried to build the hybrid model, as I mentioned earlier, wherein you are using both the plant tower and OPC, and then we developed the this is a locally calibrated model which we developed. So here what you could see is that the bias has drastically decreased, and the errors also have decreased. So that means it is a better model which when compared to the using a single OPs, I would say do not use a plant, do not report a plant tower, PM10 from a plant tower. And additionally, OPCs are good, but having a combination of both can actually be a best solution when it comes to reporting PM10. Now, when you look at this combination, now let's see for PM2.5 how various algorithms can actually work. So here in these plots, all of these plots have the x-axis being reported. That is the reference instruments, and on the y-axis you have the sensors reported PM2.5. So each of these plots, you will be seeing that there is a linear. So initially, so that you have both the sensor-wise as well as generalized model. So you have the linear regression, generalized sensor-wise, then you have the quadratic regression, random forest, support vector, XGBoost. So all these things, all this something which we looked over an year. Now, the main thing to be noted here. Now, I told earlier, the majority of the people just consider R square greater than 0.7 is the best PM sensor. Now, let's see which are the models that gave me R square greater than 0.7. So here you have the linear regression generalized, which is R square 0.74, random forest regression sensor-wise with R square 0.74. Then you have the random forest generalized model R square 0.75, XGBoost regression with R square 0.75. So these four models are giving me an R square of 0.75. So suppose if I have consider only 0.75 R square value, then these are the four models that I'll be selecting. Now let's look into what the sensor with the reference instrument scatter plot shows. Let's focus on the random forest and XGBoost. So here you could notice that where there is a sharp cutoff below this, say I think it will be around 15 microgram per meter cube around, which we are seeing a sharp cutoff. Now, why does this has happened? Now, just an R square cannot actually tell you which is the best model, right? Now, but generally, there are papers which have published that random forest model can be a good option. But the scenario here is what is specific to our location. So in India, in the winter season, what happens is you are having a very high concentration. So PM2.5 can actually go above 100 microgram per meter cube. And in the monsoon time, the PM2.5 can go actually below 10 microgram per meter cube. So you're having a very huge variation with respect to season in India. Now, what happened is we developed this calibration model during the winter season when we were having high concentrations. So it was not the machine learning algorithm that made the mistake. The thing was that our calibration season which we chose was a high concentration period. Now, what does machine learning algorithms like random forest regression does? They try to fit whatever the training data set you have. Now, if you are considering the top part just alone, if you remove all this, then if you look at the particular training data set and then compare it, it would have given the best model. And then we could have said, but when we are having very low period, because we were evaluating over an year, what we saw is that at the lower period, this random forest regression doesn't work, or the machine learning algorithms like XGBoost also doesn't work. But however, linear regression worked for us here because linear regression has a flexibility that it can actually interpolate. I mean, it can actually extrapolate. So it extrapolated above the training data set, which helped us to capture and which helped us to give a comparatively better performance with less bias in the case of comparing all these models. So main thing which we need to notice, we can try different models, but what suits us is one of the things which we need to analyze. So what this is an example just from the PM 2.5, but when it comes to the gases, one of the things we noticed is that same things can happen. Like in some particular season, there might be a particular model that is performed better, but in another particular season, there is another particular algorithm that can work. So these are things which we need to see when we are choosing the models. Now let's see something regarding the gas sensors. When you compare the manufacturer calibrated data or the factory calibrated data, which is the level 1 which I initially introduced, to the level 2 data where you are doing a local calibration. So here in these plots, the error is in the y-axis and the correlation is marked in the x-axis. So the more closer you are coming to the lower left corner, it is a better performance. The colors here in the markers represents the different sensor vendors, and the range of this are because you have say 5 or more than that number of devices you are considering from each vendor. So what you notice in the so in the top you have the NO2, bottom you have the ozone. So you are seeing that the correlation can be there is a high the correlation is extending even to less than 0.2 correlation. You are getting with certain or factory calibrated data. But now if you're applying a local calibration, considering the cross sensitivity, considering the different model inputs, like say for NO2, you can consider ozone, CO values from the particular environment where you want to put the sensor. What we observed is that the error can actually decrease to 20 to 40% in the case of NO2, and in the case of ozone, it can actually reduce less than 20%. And also the correlation has also improved greater than 0.7 in both the cases. Now let's see. So now you are we are in a way that we can actually trust the calibration models. But here comes another tweak. Say that this I'm taking it from the Jiao et al, where you are seeing that on the first column it is the raw data, and the second column is calibrated data. This is for the NO2 value. So you have in the y-axis here, in the y-axis it is the reference NO2 concentrations in ppb, and on the x-axis first you have the raw signals, that is a millivolt, and then in the second part you have the concentrations in ppb. So here this is this is the aging which Jiao et al has looked into, the aging of the NO2 alpha sense gas sensors. So initially what you see here is that your raw data is linear and your calibration data is looking fine. Things are all good. But now let's see what happened on the 961st day. Still, your R square is somewhat fine. Like it's R square, at least you are having a R square of 0.53 for your calibrated model. But when you look at the sensor, it's actually just clumsier. It just has a globe. You have just seen the data point just shattered. The linearity has been lost. That means sensor has aged. A sensor has gone, the NO2 sensor is aged, NO2 sensor has gone bad, but your calibration model worked well. So now if you were comparing just the calibrated data with your reference instrument, you would always say that, yeah, my sensor is working fine even at this stage. But what is actually driving this? Your NO2 sensor has gone bad because NO2 sensor is actually, your NO2 and ozone sensors are similar, but NO2 sensor is just with an ozone scrubber. So as the ozone scrubber has depleted, your NO2 sensor's performance also would have depleted. And while your model is actually built with different calibration model, it's not just the NO2 that has derived. It can be the ozone or the CO or the RH or the temperature, different other model inputs which you have which you have put into the model, which would have derived which would have given you good reasonable results in the case of the NO2 concentrations. So the main thing here is that we need to make sure that your sensors are working fine, not just comparing the calibrated data values. Now, since we have to deal with all these different sets of data, the main so it was a big for us it was like we have to start from the scratch, fetch the data, do the standardization, do this testing. So what we did is we developed a data management system, and in GitHub we have actually released the codes for developing this data management system to handle the data in a very proper way, like from fetching the data through the API, getting it in the JSON format, to standardizing, then applying the machine learning algorithms for calibration and seeing the QC calibrated data available. We have actually developed the codes for it, and it's available in GitHub. So I'll welcome each of you. You can just have a look to it. So as a recommendations, what I would like to say is that when you have to you have to collocate and evaluate sensors before deployment, that is the initial phase, to make sure you are using the proper sensor. It's not that sensor. If just remember that it's never the sensor that the moment you start recording is not when the sensor is actually activated. It's moment you have unpacked from the unpacked that the sensor started recording. And they always make sure you directly correlate the raw signals with the reference concentrations, and it's not just a calibrated data that we need to actually see. Also, assess the long-term sensor and calibration model performance, because what works for one location might not work for other location, and what works for one season might not work for another season. And while we're reporting PM10, using a combination of OPC and Panther can give a better performance. And having site-specific calibration models, like what you saw in the case of NO2 and ozone sensor, it can actually improve your it can actually decrease your errors and improve your sensor performance. And the main thing is, while you're dealing with calibration models, make sure you're using the machine learning algorithms wisely. Not just that you are relying on the metrics that you see, but make sure that the data is make sure that it's not just the R-square that matters. Different metrics are developed, and also a simple scatter plot can actually give you a better representation of, even if you do not know whatever other the metrics would be. So with that, I would like to end, and I would like to invite you all to look into our flagship event from CSTEP, that is the India Clean Air Summit ICAS 2026, to know more about the air quality management that is currently happening in India. So with that, yeah, thank you.
Thanks, Emil. Really great presentation with all the details and the data that has been presented. So now we open the floor again to questions coming from our audience. Anyone who wants to start with the questions? Ik, do you want to go? I find it quite surprising, really, to learn that the gas sensors deteriorate really fast. So when you talk about the alpha sense as one of the options for, well, alpha sense are in a way very sensitive in terms of the levels of concentration that they can measure. They can be, how do you say it, pricey compared to alternatives. So when they go bad in 6 months, is there a way for you to somehow extend its effectiveness beyond 6 months? Emil, have you done anything about that? And then we can have Mohammed. Ik.
Yeah. So mainly why it has gone bad with the 6 months for us is that because of the concentrations that is there in India. So the location where we had the sensor, so we are very like the major, like it is in Bangalore, where it's a metropolitan city. So now you consider NO2 concentrations over a day. There are, even in the monsoon times, you will have the high concentrations, like it is above around 40 ppb above is what you can actually see in majority of the time. While in the case of even ozone, say that if you're putting the ozone sensor in a summer period, ozone concentrations in India can actually go to greater than 100 ppb. While it is in a monsoon, it can actually go even below 20 ppb. So suppose suppose what happened is, in our case, we put the sensor, we started the sensors deployment in winter. Say the initial collocation was in winter. Now we are crossing the summer, where you have the high concentration of ozone, and then moving to the monsoon. So by the time, so that's main reason what has happened. Like the seasonal changes has actually lead to the depletion of the sensors more. So suppose, since I had this intuition in my mind, what we did is that we actually later put the started a sensor, putting it up in the monsoon period, where you have the lower concentrations, and then try to see what is happening over. So when you are actually starting putting the sensor in the monsoon, where you then move to a different way, then actually a little bit more you were we were able to, like, from 6 to 8 months, it was a little bit more depending on the concentrations that we were able to. So it is just that if you're putting the gas sensors in a location where there is very less concentrations, the life can actually be increased.
Okay. Thanks for those insights, Emil. Eek?
Based on what you've found in your study, do you think essentially this is a function of the performance envelope of that sensor not being optimized for the particular environment in Bengaluru? And do you think we should be asking manufacturers to produce regional specific subcells? I don't mean the overall package, but essentially underneath all of that, most commercial units are based on 3 or 4 manufacturers and 3 or 4 techniques.
Yeah.
Saying that we need to have a high humidity, high temperature, high concentration version of the same sensor package for use in India or use in sub-Saharan Africa. We need to have a version which can cope with solar insolation better. Do you want to comment on that?
Yeah, that's a really good thing. But I think over even if we look back, like 10 to 20 years back also, it is the same manufacturer that is still functioning right now. So like, I don't think like new technologies or new there are sensor vendors that are coming up, but still inside, when you look in the integrated ones, are just Alpha Sense, or you have the plant hours. So it's just that they are the ones who are ruling. So yeah, I think maybe they should try it out.
Thanks for the question, Eek. We have a chat question. So this from Glidine. So if IndiSet were to be replicated in another city with even fewer resources, what part of the calibration protocol would you keep as non-negotiable? And how transferable were the calibration models across different sites and seasons? So really interesting question. Thanks, Glidine.
Okay, yeah, thank you, Clyden. So the thing is, since we observed this, local calibrations can improve. And one more thing we noticed is that these sensor manufacturers, like in India, we have a very different type of environment. Like in southern part, it's a different, the climates are different, the weather, the pollution sources are different. Now, if you go to the northern part of India, then you have a completely different environment, I would say. And because of this, what we noticed that even the sensor manufacturers, which we initially looked into, the 5 vendors, were actually calibrating their sensors in different parts of India. Like we had from the southern part, we had from the western side, eastern side, northern sides, and they had these factory calibrations done. Few of them even mentioned that they were doing it in their outside environment and developing their models. Now, when we looked into when we checked it in Bangalore's environment, majority of them failed, as you could see in the case of the gas sensors. While what happened in Bangalore was like the locally calibrated improved. So because of this understanding, what we thought is that the IndiSet facility itself has to have multiple branches in multiple sites in India. So we have been looking into different different environments where we can put up such facilities, where you have the reference instruments. Like in the eastern, on the western side, you have the Rajasthan, which is more of the dusty area, like you have the deserts there, so you have the coarser particles more. Now, when you look at the eastern part of India, you have this IGP, or northeastern part, you have the IGP part. So northern part, where you have the high concentrations, which will be like something which we can look into for the high pollution loads. And say that we have the marine environments where you are again seeing a marine coats aerosols coming up. So these different PM compositions or different pollution sources itself can actually affect the sensor performance. So there is actually a need itself that we need to have sensor evaluation facilities at different environments, so that it's not that every city has a sensor evaluation facility, but at least different environments has a sensor evaluation facility to look into the sensors and see how the performance can change. And also when you have ACSM, which is a chemical composition, something which we are looking right now is how the ACSM with the real-time chemical composition can affect your sensor performance. So these are things which are currently, which we are under research from our end. So that's what I would say. Like it's something which we'll be looking forward.
Yeah, thanks. I mean, other questions from our audience? About the PM10 work that you presented. How did you come about in decide how did you decide on combining the OPC and the plant tower measurements to be able to combine them and have better performance? So were there any criteria that was considered in, combining those two, for example?
So with previous research papers which we looked into, initially we knew that the alpha sense OPCs can have a better performance in the coarser particles. So that was a research papers we looked into. And then because of that, we suggested the sensor vendors who were providing us sensors to have these combinations so that we can actually compare. So it was there something that we asked them that we need this. It was just for our purpose. Like we just so that you try to give us both the one. We need plant tower and alpha sense OPC so that we can develop our own calibration models. And the sensor manufacturers, like they were welcoming, like they would also like us to do the research. And so they were like, okay, yeah, we can give a try. So from that only then, and with that, we try to develop the different types of models. Like if you are using just a plant tower, what will the output would be? If you're just using an OPC, what would the output be? And if you're using a hybrid model, what can the output be? So over time, over the whole year, we try to look into what the performance of each types of models. And then that's a way that we came to a conclusion that as a combination of we use, that can be the best. And the second, and if you do not have that much, then better that you go for an OPC rather than a plant tower. Because generally the plant tower actually doesn't really report PM10. It's just actually, it's an just equating it to the PM2.5, PM1, and then making the subsequent values. So that's something which we need to understand, that we are not actually recording the PM10.
Yeah, that's true. That's true. Yeah, Fernando.
In that sense, I have a question, because those instruments, the plant tower and the alpha sense, has different drift. So how do you consider this drift in different conditions?
Yeah, really great question.
So yeah, so mainly what we looked into right now is how we can like compare it with the reference instrument and see whether we can use it for our purpose or not. That was our main agenda. Like because we have right now a sensor network in Bangalore, where we were looking into how frequently we need to change the things. How can we make sure that we operate the sensor network throughout the year, or more than like it's the sensor network is right now operational since last 2024. So it's like more than nearly two years around we are trying to maintain it. And that's main thing we understood is that better thing is just frequently have these collocations. Say that you are doing a collocation for 15 days, or say let it be, even if it is a 7 days collocation, bringing back a few sensors back to your reference system. That was easiest thing which we had in hand, that bring 5 of them and just see the collocation. If your metrics are working fine, then you go for it. Or if it's not, if your metrics are not looking good, or your scatter plot is going away, better that you remove the sensor. Because in the case of plant tower, the easy things what we notice is that plant towers it's going dead can be easily identified. Sometimes you will get a 3000 just stuck there, or you might get a 0 value. It's just that it's not, it's like a sudden moment itself you'll understand the sensor has gone bad. And our QC, we have developed a QC system where automatically we can see that if it is within if the sensor reported is not within a particular threshold, we get alerts. so that we know that we have to continuously check that particular sensor node and bring it back and have this evaluation. So that's how we were dealing with our the sensor drifting in our network.
Okay, because once I faced the same situation, I decided to consider the weather conditions, relative humidity, wind, and sunshine, put all together in a random forest model, and I get a really good correlation. Not consider another PM2.5 sensor, just consider the same ambient conditions, and that improve a lot because the plant tower sensors also has a relative humidity and temperature sensor inside the instrument, so we can make this better model.
Yeah, I agree to that part. Like, because one thing is that this when you measure the plant PM, always hygroscopicity is something which is always there. So definitely, like in our case also, we looked into the RH because our initial model itself also considered the relative humidity in the case of PM. And in the case of gases, we looked at the different other gases. Like in the case of ozone, we had NO2, ozone, CO, and also temperature. So these parameters were also looked into, and as I mentioned in GeoVital, sometimes what happens is even if your NO2 sensor is gone bad, the thing is that your calibration model will work because the other parameters which you have inputted into your model might be working and they would be driving your model. So it's always a good thing that you can do is while you are developing a calibration model, try to understand which is that particular input or the particular input which is driving your model the most. It can be sometimes, it might not be exactly that for an NO2 sensor that NO2 itself is driving. Sometimes it can be the temperature that is driving your model completely. So even if your NO2 sensor has drifted, if suppose the temperature was driving your model, your calibration model would actually work fine. So having a comparison, always checking whether your actual sensor is reporting can be the best thing, rather than having a multiple calibrations over a like drifted sensor. That would be my suggestion for it.
Yeah, I guess you always have to look into the raw data as well. Yeah, sorry. Yes, Ik, and then we'll have a chat question from Julius. Go, Ik. Thank you.
I have a quick question and a quick comment as well. The question is about, you talked about getting a manufacturer, getting a system built around two particular sensors, manufacturers, and then using those. Do you want to comment on the fact that even within the same batch, two sensors from the same manufacturer don't necessarily work well together, but also they can be, the performance can be, shall we say, affected by how, Richard, you'll appreciate this, how the electronics is set up, how the ground plane is set up, how the inlet is set up. Would you like to comment on that as being an additional factor?
Yeah, definitely. If your particles are not able to transfer properly through the inside of the optics, then things change. So that is the main, like if you generally, I think the Terra sensor, which is one of the Terra sensor, something which I recently, like I was looking into, that they were claiming that they can actually report PM10 because of they have a fan and they are able to the PM10 was able to go properly. That was through the inlet. So, but what happens is when we were evaluating in our conditions, we noticed that Terra sensor can actually performs only similar to a plant tower rather than an OPC. So definitely with what pressure that each particles are being pushed, sucked into the system, and the way the particles move through inside the each sensor actually plays a major role in the performance of this in how it can see the different particles. Yeah.
Okay. Thanks, Emil. Can we take the question from Julius? Can you share your insights on monitoring VOC and calibration of VOC sensors? I know it was not part of the presentation. So what are the important considerations in working with VOC sensors?
Okay. When it comes to VOC sensors, I think I won't be the right person because I have not looked into it.
I can comment if it's helpful.
Yeah, I know.
Yeah, please.
So
Go, Ik.
when you're talking about VOCs in this context, I'm assuming you're talking about total VOCs using PID
Yeah.
sensors. And we have to remember that the PID sensor for VOCs is usually targeting one particular VOC as its reference, and then looking at a lookup table for relative response to other VOCs. So I think, from the top of my head, they tend to focus on 1,3-butadiene, and then everything else is ratiometric in terms of response to that species. So you're always going to be saying, I'm measuring total VOCs, and I have an understanding of how that relates then to other VOCs within that particular table that the manufacturer is using. And also the sensitivity will change depending on which particular lamp they're using, which strength of lamp, 0.7 electron volts or 10.2, 10.4, whatever it happens to be. And that'll change the behavior to the relative behavior to the other VOCs in that category. So I think VOCs are not quite, in terms of speciated VOCs, without having some sort of front end and a different type of sensor perhaps, it's hard to say that they're as mature as, say, an OPC is, unless you're looking to say the total VOCs are above a certain amount in a certain environment. So VOCs is tricky.
Yeah. What I've seen, at least, are executions where they have multiple VOC sensors to be able to try to capture the different species. But yeah, I guess that's an ongoing, type of execution, and we need to wait on how they're using it both for outdoor and indoor applications, because they have very different environments. So we have another question from Fernando, and this is about the use of electrochemical sensors. Yes, they're bad, and because of its rapid degradation, is it still worth buying? I guess this is a question that can be addressed to both of you. But yeah, who would want to answer this?
To you, Emil.
Okay. Yeah. Okay. Yeah. So I would say that it is worth to buy because you can actually see I would say it is still in the study. Like certain times, say that you want to just capture certain episodes that we are looking into, or say if you are in the near to a source that you want to capture, say that you are in a high concentration, say when the NO2 values are like greater than 40 ppb is what you are expecting that area, then in that cases, electrochemical gas sensors can actually give you better results when properly dealt with the data. But yeah, as I mentioned, the rapid degradation was mainly, in our case, it was mainly because of the very high concentrations that we were exposed to. So as I mentioned earlier, while Richard was also discussing on this, it was that if the time when we started the initial starting when we considered it in the monsoon time with the low concentration, where even the ozone values were lower, the things were changed. Like it was working for more than 6 to 8 months. So it just depends that the way we started was a difference compared to what was happening. So I think it can also add to this.
Absolutely, and it depends where you're deploying them, and they can have very different lifetimes. There's not exactly this many months or that many months, which goes back to the residuals and error points from earlier on. But I think we have to think about it as a cost proposition, essentially. What we're doing is not generating, well, we're trying to generate data. That's the value at the end of it. And if that value is doing what you need it to do based on the costs you have and the available equipment you have, then yes, they're worth it. But if you're looking to get reference grade NO2 straight off the bat with no co-location, nothing else, then they're not going to do what you want, regardless of how much money you spend on them. So I think it's, in many cases, we need to take a step back and consider what is actually required for that scientific or social need in that location at that time, and then go back and say, this is how much it's likely to cost over the lifetime of the deployment, not just right at the purchase price, but the operational costs, the compute overheads, that kind of things. So it's not answering your question, it's adding more questions to your question. But I think it's, again, going back to some of the documentation, the WMO documentation really talks about it in nice, concise detail.
Yeah, thanks, Emil. Thanks, Ik. Other questions from our audience? Emil, so how big is the sensor network that we have in Bangalore?
Yeah, so currently we have a 45 node multi-potent glucose sensor network that is um, like 45 of them from different manufacturers, and it can measure PM 2.5, PM10, NO2, ozone, and CO. So
Okay.
the thing is, the target area was around 2,200 square kilometers, but that was the initial start that we thought that we'll just start with some 40 or 50 of them, and then see how the performance is, and then move ahead with it.
Okay. Are there any plans to expand that in, say, the next year?
Yeah, we are looking for expansions also, because certain areas like certain we were able to capture only 2 industrial locations mainly. So we would actually want to see put different multiple sensors in the downwind side, upwind side, and also in different industrial locations, and see how the performance would be. So these are things which we are actually looking forward to.
Okay, that's really, really encouraging and inspiring. Really need more resources to be able to, have these types of deployments in other cities.
Yeah.
Okay. It seems that there are no more questions. I guess before we end the webinar, do you have, any final messages, Ik or Emil, to the audience? Sorry, I might be putting you on the spot, but
After you, Emil, please.
Yeah, so I would always say that understand what type of data that comes to you, rather than just like understanding what is the error that can each data point can, like each data can give you, understanding what's extent you are dealing with, like are you dealing with the raw data, are you dealing with the factory calibrated data, or is it the locally calibrated data, what's the type of data that you're dealing with, what's the error that can be associated with dealing with the different sensors. So understanding these factors can be really important, and at the same time understanding how the machine learning algorithms can change over time, or what your training data set can how the training data set can influence your machine learning algorithms. So keeping in mind all these things can help us and look into dealing with sensor data more wisely, I would say, because if you blindly just believe that something is right, something might not be right. So you need to know where you are going. At least you need to know how much error is there in what you're doing, and that confidence is required when you're dealing with sensor data, because otherwise it's that otherwise then it should always be that we should know what exactly we are reporting and to what extent our things can go right and wrong. So that's what my main suggestion would be.
Thanks, Emil. Thanks, Emil. Ik?
Just to echo what's been raised there, it's about considering what you're trying to do, where you're trying to do it, and what you want to get out at the end. So there's no hard and fast set of absolute rules or a lookup table that says I'm trying to do this, therefore I should do. It's very much a judgment call on what you're trying to do. And if it's something which is relatively new to yourself, reach out to the Allin-Wayra community. Everyone's very friendly, very helpful, and have a lot of experience. So we don't have to be reinventing the wheel every time. That's the whole point of this community. So please use it, be active in it, and you get involved with the activities such as the conference meetings, because the side meetings at the conference about these kind of things are fantastically useful. So I can only recommend further communication.
Yeah. I guess learning from each other is the critical thing here. We each have our own unique setups, unique situations. And I would like to echo what Ik said earlier, that there are no prescribed strategies that are really work best. It really deals, or you really need to focus on how data is how do I articulate this? Before, I always thought that, if you just see a correlation and that's it. But once you start slicing the occurrences, and then, looking at the trends, you start understanding that, oh, there are different behaviors for a day, for a week, or for several weeks. And, trying to apply a machine learning model that is just a black box may not be the best approach. You need to be able to understand how or what the limitations are for these models, so that you know when these models would be best fitted. And what Emil has showed us earlier was that even if they tried using, say, RF or XGBoost, in the end, the linear regression works perfectly fine for some of the cases that they have. But ultimately, it's having several different types of models and being able to evaluate them and finding a good spot, or a good set of parameters might be the best approach. And there are no prescribed solutions at the moment. But having this type of community, I think, is very helpful in allowing us to get that confidence and knowing that we are doing the right approach. And with that, I'm really thankful to Allin-Wayra for allowing me to communicate with experts like Ik and Emil, and helping us or guiding us in our own efforts here in Manila. And hearing from our audience earlier, learning from their own experiences has really allowed me to imagine how we might be doing things, say, in the mountain ranges here in the Philippines. But I hope you will continue to reach out to us. We'll have more sessions like this in the future. Do suggest topics that you might want to us to consider and plan out in the future. And with that, thank you. Thank you. I think we've almost reached 2 hours for this webinar. But really, I'm really thankful to Muhammad and Emil for their valuable time to be with us today, so that they can share their experiences and their efforts, both in the UK and India. And I hope everybody has learned a thing or two in the efforts that they're doing. Let's continue to work together. Let's continue to learn from each other. With that, thank you very much. Good night from the Philippines. And see you soon in our next webinar. Thanks, Ik. Thanks, Emil. Thanks, everyone. Let's continue watching the World Cup. So good night. Good night. See you in our next webinar. Thank you.